Okay, I guess we've given a couple of minutes to the latecomers. So let's start. Welcome everybody to the first analysis seminar of this semester at the Institute for Advanced Study. And our first speaker of this semester is going to be Robert. So Robert Young, who's currently a member, and he's faculty at the New York University. And he will talk about filling multiples of embedded curves and quantifying non-orientability.
Thanks.
Please.
Thanks for inviting me. It's great to be here. So, like I said in the chat, I dropped a link to the slides in the chat. You can find them at this address here, because I don't know, just in case you want to flip around in them, or just in case the screen share is a little blurry. But yeah, so I want to talk about filling multiples of embedded curves and quantifying non-orientability. And so let me start by saying a couple words about the title. The idea here is that, so filling multiples of embedded curves is kind of the problem that got me interested in this. So if you have a curve in the plane, say like that, let's call it T, then there's some minimal surface whose boundary is that curve. And you can talk about the filling area of the curve to be the area of that minimal surface. Then if you take the curve and you multiply it by 2, if you take 2 copies of the curve, you can ask, okay, if you take 2 copies of the curve, what happens to the minimal surface? And the obvious thing would be, if you take 2 copies of the curve, you should get 2 copies of the minimal surface. But it turns out that that's not always the case. Sometimes the optimal filling for 2 copies of the curve is different from the optimal filling of 1 copy of the curve. And the first example of this was due to L.C. Young in the 60s. And so the way where non-orientability comes in is that the L.C. Young's example was basically based on the fact that you can embed non-orientable surfaces in Rn. And L.C. Young's example was a curve drawn on a non-orientable surface. And the fact that the filling area of that curve was so different from the filling area of its double is because of that non-orientability. So what I want to do today is a couple things. I want to give an example of this phenomenon where the minimal surface of T is different from the minimal surface of 2T. I want to explain how this is connected to orientability. I want to give a way of quantifying non-orientability, and then I want to show how you can bound the non-orientability of a surface using uniform rectifiability. So a couple of different things. So yeah, it's a small group, so feel free to ask questions. I'll pause for questions at regular intervals, and yeah, I have the chat open on my screen if you want to ask a question in chat. But is that okay so far? Anything so far? Okay, so let's start with the definition. If T is an integral 1 cycle, which you can think of as just a union of oriented closed curves in Rn, we define the filling area of T, Fa of T, to be the minimal area of an integral 2 chain of a surface with boundary T. And the main question I want to address today is the following. How is the filling area of T related to the filling area of 2T? How's the filling area of a curve related to the filling area of 2 copies of that curve? One direction is clear. If I have a curve T, and if I have a minimal surface whose boundary is T, then I take 2 copies of that minimal surface. I get a surface, at least, whose boundary is 2T. So the filling area of 2T is always at most twice the filling area of T. I can always fill 2T with 2 copies of a filling of T. And in low dimensions, this is sharp. When the ambient dimension is low, this is sharp. So for instance, if n is equal to 2, if you have a curve in the plane, then the filling area of 2T is equal to twice the filling area of T, because, well, in the plane, filling area is mostly a question of winding number. If I have a curve like this is my T, then it has winding number 1 around this region, 1 around this region, 1 around this region, 2 around this region. And so the filling area is the sum of the areas of these regions plus twice the area of the center. If I go around the curve twice, all my winding numbers double. And so I get 2 times this, plus 2 times this, plus 2 times this, plus 4 times this, which is twice what I had before. So in 2 dimensions, filling area of 2t is equal to twice the filling area of t because you have a nice formula for filling area in terms of winding number. It still holds in 3 dimensions. If you have a curve in R3, then the filling area of 2t is twice the filling area of t. But this takes more work. This is a theorem of Federer from the 70s. And if you go to higher dimensions, it starts to break down. Like I said in the introduction, there's a curve t in R4 where the filling area of 2t is only about 1.5 times the filling area of t. Elsie Young, he said that the curves like this were sort of cheaper by the dozen. That sort of if you want to fill 2 copies of this curve, you get the second one for half price, for half the extra area.
What's the smallest you could make that number?
Yeah, that's the question. That's what I want to talk about today.
Oh, okay, sorry.
But we'll get to that. But let me start by just showing you what this example looks like and showing you how to construct an example like this. So like I said, this example is related to the fact that you can embed non-orientable surfaces in R4, but not in R3. And so we construct this example based on an embedded non-orientable surface. So let's take, say, a Klein bottle in R4, like so. And then I'm going to construct a curve on this Klein bottle by drawing an odd number of loops, 2k plus 1 loops on the Klein bottle, and orienting them in alternate directions. So you can see it goes left, or it goes back and forth and back and forth and back and forth as you go around the Klein bottle. Here, it's important that we have a non-orientable surface because, well, we have an odd number of loops. And so as we go around, we change direction an odd number of times. And then 1 extra time from the twist in the Klein bottle, from the gluing with the twist. And so overall, we change direction an even number of times, and that means that we end up going the same direction that we started. We can have these alternate all the way around, right? So if this is our curve, then what does the minimal filling of this curve look like? Well, whenever we have 2 loops like this going in opposite directions, we can fill the area in between them with a disk, with a cylinder, with a band like so. And so we can construct a filling of this curve by just pairing up these curves 2 by 2 by 2 by 2 by 2, and filling the area between each pair of curves with a cylinder. And the only problem with that is because we started with an odd number of curves, because we started with 2k plus 1 curves, we're going to get k cylinders, and then we're going to have 1 disk left over, 1 curve left over, and we have to fill that curve with a disk. And if we do that, we get a filling of t, where the area of that filling is roughly half the area of the Klein bottle plus the area of that extra disk. And this is more or less optimal. When k is large, this is more or less optimal. The filling area is roughly half the area of the Klein bottle plus the area of that extra disk. Now, when we double t, when we take 2 copies of t, that means we have 2 copies of each loop. That means now we have an even number of loops. And because we have an even number of loops, we can pair them all up. We can pair all the loops up, and we can fill the region between each pair of loops by a cylinder, and we get 2k plus 1 cylinders going all the way around the Klein bottle and going in opposite directions. So you can see it goes counterclockwise, then clockwise, counterclockwise, counterclockwise, counterclockwise. It alternates all the way around. And then because of the twist in the Klein bottle, we get 1 extra flip. And so we get an even number of flips total. So that gives us a filling of 2t consisting of 2k plus 1 bands. Those bands take up the entire Klein bottle, so the filling area is roughly the area of the Klein bottle. Again, that's pretty close to minimal when k is large. And furthermore, this is less than twice the area of the of t, less than twice the filling area of t, because we don't have to have that extra disk. The filling area of 2t is less than twice the filling area of t by a factor of 2 copies of the disk. And so that 1.5 or that 1.52 from the previous slide is basically trying to figure out, okay, how can you embed a non-orientable surface into R4 so that the area of the surface is as small as possible, but the area of this extra disk is as large as possible. Okay.
So how does he get actually to the actual number, to the 0.52?
I've never actually done the calculation. So his example is different than my example. He actually uses a projective plane instead of a Klein bottle. And so I think he just picks a particularly nice embedding of the projective plane and then does a calculation.
You're taking kind of Brian's example?
Might be. I don't remember.
Because I think that is like the version of Brian White. But then I was always curious how he gets to the 0.52. Why can't he get 1.5 exactly?
I mean, it's some fraction with the exact number in the paper is I forget, it's 2 plus pi over pi or something like that.
Something like that. So it's a little bit more meaningful.
So we have to sit here and wait and wonder how small this number is going to be. All right, you guys know.
Well, I'll tell you one slide. Give me one slide. So, but yeah, you have a point there, which is that once you know that there's not an equality here, the natural question is, okay, is there what is the relationship? Is there some constant so that the filling area of 2t is bounded below by c times the filling area of t? And the answer is yes. For any d and n, there's some c greater than 0, such that if t is a d cycle in Rn, then the filling area of 2t is at least c times the filling area of t. Unfortunately, the proof gives you not really a great idea of what that constant is. All you know is that it's greater than 0. You don't know, for instance, that it's greater than 1. Very likely, if you actually went through all the calculations in the proof, you would probably get some vanishingly small but positive number. So
wait a minute, it could be 1, right?
It could be, as far as we know, it could be 1, but
that's what you would guess, right?
Yeah, I mean that's what you would guess, but we have no. We have no evidence either way.
Totally open. But Peter, can I give you a little anecdote on this? So
I know nothing about it. So yeah.
Sitting in my office, there's a big folder that I got from Gene Taylor. And Arngren was actually trying to work out this proof that Robert has solved for decades. Together with Bombieri, actually.
Oh, okay. Fantastic.
And that, I mean, it's completely crazy. Robert got this wonderful result with a proof, which is just a positive constant, and it's completely crazy. You would say, yeah, at least it shouldn't be cheaper than filling the single guy, but we don't even know that.
So even for n equals 2 and d, whatever your example was there, you don't know your constant.
So you mean what's the best version?
No, what your proof gives a number.
Yeah, the proof gives a number, but the number even in this dimension, the number would be just something very, very small.
Okay.
I mean, the usual thing I say about the constant is that I didn't even try to figure out what the constant is, because it would mean going through 50 pages of my paper plus in the middle of my paper I use a monograph of David and Semmes, which is another 100-some pages. So it's whatever constant you get to after after doing that much work. But yeah, so we can ask whether it's bounded below by some function of the filling area of t. In fact, it's bounded below by a constant times the filling area of t. And what I want to do today is I want to try to explain why this is. I want to try to prove this fact. Okay.
Just before you give the proof, on the other hand, has anybody improved the Young example, which makes C, what's the smallest C you know?
I have not actually. I haven't tried to do the calculation. I don't know. I don't know. I mean, I can tell
So
you.
like in dimension 2, all we know, say if these fixed, is his example, say his example with whatever he wrote down, and Camilo was saying he didn't know where it came from, and your existential lower bound. That's all.
Yeah, I can tell you later on. Later on, we'll get to an example of a surface or an example of a sort of construction that I suspect gives
Optimal.
something optimal,
Okay.
or at least relatively close to
All right,
optimal.
I'm staying on. I'm staying on.
Yeah, but yeah, I haven't actually tried to do a calculation. Okay. Okay. Shall I continue? Okay. So I want to try to prove this. The basic idea of the proof is that we want to the basic idea of the proof is that we want to take a filling of 2t and divide it in half. We want to be able to we want to be able to show that if you have a filling of 2t, then you can produce a filling of t that's where the size of that filling of t is bounded by a constant times the size of the filling of 2t. You want to cut a filling of 2t in half. And so this is maybe a little clearer if I show you an example. And the easiest example to see is in dimension 0. So if you have a 0 chain, that's a collection of points with positive signs and negative signs. And a filling of a 0 chain is a collection of arrows where you have an arrow coming out of each minus and an arrow going into each plus. So a filling of twice this 0 chain is going to look like this. You're going to have 2 arrows coming out of each minus and 2 arrows going into each plus. So if you have a filling like this, how can you cut it in half? Well, one thing you could do is you could just take every other arrow along this loop. You take every other arrow along this loop, that's half of the arrows, and in fact, that's 1 arrow coming out of each minus, 1 arrow going into each plus. But that's a little bit difficult to generalize to higher dimensions, and we're really interested in what happens in higher dimensions. So let me restate this in a way that's a little easier to generalize. So another way to look at this is that, well, the important thing about this filling of 2t is that this is a loop. This is a 1 cycle, and it has to be a 1 cycle because if you take its boundary mod 2, well, its boundary is 2t. 2t mod 2 is 0. So the boundary of this filling mod 2 is 0. The filling is a cycle mod 2. It's a loop like this. If you have a loop, it can be oriented like so. Let's call that orientation T. And then you can get that half of the filling by taking the sum of the filling plus the orientation. And if you do that, then places where the filling agrees with the orientation, so the orientation is going sort of counterclockwise like that, places in the filling that are going counterclockwise show up in the sum. Places in the filling that go against the orientation, that go clockwise, get canceled out in the sum. And so what you end up with is twice a filling of T. And this is something that we can generalize to higher dimensions. So for example, if we try to apply this to the Klein bottle example from before, well, remember our Klein bottle example, we had this cycle T drawn on the Klein bottle. We had this filling of 2T, call it B, which is made up of all these cylinders with opposite orientations. If you consider this mod 2, if you drop the orientations on these pieces, you end up with a mod 2 cycle. A mod 2 cycle is just a surface in Rn. In this case, it's the Klein bottle in Rn. Now, the next step in dimension 0 was to take an orientation of this mod 2 cycle. We can't quite do that here because this is a Klein bottle, this is non-orientable. But what we can do is we can construct something I call a pseudo-orientation. A pseudo-orientation is just an integral cycle, which is congruent to the filling mod 2. And the way we can construct that is we can take our Klein bottle if we cut the Klein bottle right along, right through the neck like that, then we get a cylinder. If we cap off the ends of the cylinder, we get a sphere, and a sphere is certainly orientable. So we take an orientation on that sphere, and we get an orientation on the Klein bottle, plus those two disks that we added, to cap off the Klein bottle. This is an integer cycle. Its boundary is 0. It's congruent to P mod 2 because it has multiplicity 1 on the surface of the Klein bottle. It's multiplicity 2 in this extra disk. And we can do exactly the same thing with it that we did before. If we take our filling plus the pseudo-orientation, that has to be congruent to 0 mod 2. If it's congruent to 0 mod 2, that means all its coefficients are even, and that means we can divide by 2 to get something with integer coefficients. The boundary of that sum over 2 is 2t over 2 is t. And so if we take that, so if we take b plus p and divide by 2, we get a filling of t. And what that looks like is this. Here's our filling of 2t, call it b. Here's our pseudo-orientation p. And when we take the sum, again, same thing as before. Places where the orientation, which is, I guess, counterclockwise like that, where the orientation agrees with the filling get doubled. Places where the orientation disagrees with the filling cancel out, and we get 2 copies of a filling of t. And there is that extra disk. That extra disk came from that place where we cut the Klein bottle to make it into something orientable. Okay. And so what this tells us is that there's this close connection between this 2t problem and orientability, in that if we can construct a pseudo-orientation of a mod 2 cycle, then we can use that to divide a filling of 2t by 2. Is this okay so far? Are there any questions about any of this so far?
So this in particular tells you that if you're on an oriented surface to start off with, then the filling area of 2t equals twice the filling area of t.
Yeah. So if you start with a filling which produces a mod 2 cycle, if you start with a filling that produces a mod 2 cycle, which is in fact an integer cycle, which is in fact orientable, then in fact you get a little bit better. Then you can fill t with a filling which has area at most half the size of that filling of 2t.
Right.
In the zero-dimensional case that you explained, you get a purely combinatorial question. Do you know the solution to that for an arbitrary graph or in the plane?
Like if you have a bunch of minuses and pluses in the plane, what's the minimal?
Because that might tell you the complexity of your question in a higher dimension. Is that something is that trivial or?
So if I remember correctly, in higher dimensions you can approximate, or in arbitrary dimensions you can approximate filling area problems up to a constant by linear programming. Basically, you may as well.
No, so I'm just asking, since we were asking about these extremal cases, before asking the extremal case in 2 dimensions, maybe one should ask for the extremal case in 0 dimension, for which you have a pure combinatorics orientability slash, it looks like it's kind of standard graph theory question.
Yeah. Well,
anyway.
In 0 dimensions, you can always, so in 0 dimensions, you have a sharp equality, because in 0 dimensions, you're always going to end up with a 0 cycle, which is a sum of loops. But basically you have a choice of whether you take this half of the loop or the other half of the loop. And so one of those halves is going to be less than half the length of the original loop.
I guess.
Right.
Okay, it doesn't get more complicated than that. Okay.
Yeah. So this is so 0 dimensions. You have sharp equality. 0 dimensions. Because 0 dimensional things can't be non-orientable. You really only run into problems when you have non-orientability. Okay.
I would say maybe Peter's question becomes more interesting if you have a large integer, right?
Yeah.
Then you know what is the minimizer for, say, a k. It becomes combinatorially a complicated question, right?
Yeah.
I mean, which is the minimizer mod, say 9, for instance, on a plane when you have a bunch of points.
Yeah, because that's sort of a reflection of what the combinatorics of your problem is. Yeah.
But it's more relevant for larger integers,
yeah.
I think, than for. I mean, 2 is kind of easy because of the reason he explained.
The point is, I'm just trying to kind of place the problem in what kind of problem is this, and what kind of linear program is if you make the approximation. Yeah.
Yeah, I don't know. I haven't really thought about like all my examples, all the pictures I draw are mod 2 because the complications for what I'm doing are kind of the same mod 2 as mod any number. But yeah, I mean, I haven't really thought about what the picture would look like to draw extremal examples mod 3. Yeah. Is that okay? Okay. Yeah. So okay. So where are we? So if we take a filling of 2t, we forget the orientation, and then we try to orient it again to get this pseudo orientation. And so the difficulty of cutting this filling of 2t in half has to do with the size of this pseudo orientation. We get an inequality that looks basically like this. If A is a mod 2 cycle, we define the non-orientability of A as the minimum mass of a pseudo-orientation, the minimum area of an integer cycle, which is congruent A mod 2. This basically measures how hard it is to lift A to an integer cycle. And we get an inequality that if I have a filling of 2t, then the filling volume of t is at most the mass of that filling of 2t plus the non-orientability of that filling mod 2 divided by 2. And so in particular, if we want to prove our original theorem, if we want to prove this relationship between the filling volume of t and the filling volume of 2t, it suffices to bound non-orientability. It suffices to show that if A is a mod 2 d cycle in Rn, then the non-orientability of A is bounded by a constant times the mass of A. It's okay so far? Okay, so before I get to how to prove this, I want to just mention a couple of consequences, a couple of corollaries in geometric measure theory, and these are going to look very trivial, but they're not as trivial as they look. As far as we know, you need something like this in order to prove this. So for instance, if k is a positive integer, this lets you show that the map f of t is equal to kt on the space of integer flat chains is an embedding with closed image. So the integer flat chains, those are the closure of the set of polyhedral chains with respect to the flat norm. And the flat norm is not quite a norm in this situation because it's related to filling volume. And we've just seen that filling volume is not quite linear. And for the same reason, this flat norm isn't quite linear. If you take one of these Klein-Bottle examples, the flat norm of 2t is not quite twice the flat norm of t. And so it's not immediately obvious. It's not obvious a priori that the map that multiplies a chain by k is necessarily going to be an embedding. You need something like this in order to show that. Another consequence is that, well, once you know that the space of multiples of k is a closed subspace, that means you can take the quotient by it. And so one thing you can do with this is you can show that if t is a mod k current, then t is congruent to an integral current mod k. Again, this seems obvious. It seems like you should define the mod k currents to be the integer currents mod k. And in fact, you can find a couple of places in the literature where people try to do this without realizing what can go wrong. But the problem is that, well, currents are limits of polyhedral chains. The mod k currents are limits of mod k polyhedral chains. And so you can imagine that you could have a sequence of mod k polyhedral chains that converge to some limit, some mod k current. And each of those mod k polyhedral chains sort of automatically lift to integer chains. So each of the chains in that sequence lifts to an integer chain, but that sequence of lifts might not converge in the end. And so again, so this is not quite obvious. And in fact, if you go in Federer's book on geometric measure theory, he claims that this is not true. Yeah, he had an example of a mod K current, which he thought didn't lift, but it turns out that he just was he was just choosing the wrong lifts in his sequence. That in fact every mod K current lifts. So yeah. So if this meant nothing to you, that's fine. This is just I just wanted to mention this to this. Because of the relevance to geometric measure theory. So yeah, so how do we prove the theorem? How do we show that if you have a mod 2 d cycle in Rn, then the non-orientability is bounded by a constant times the mass? The basic idea is that we're going to do something roughly similar to what we did with the Klein bottle, or at least philosophically similar to what we did with the Klein bottle. So for the Klein bottle, what we did was we took our Klein bottle, we tried to cut it through the neck, and we added on these 2 extra discs. How can we do this in general? Well, in general, if I have a mod 2 d cycle in Rn, then I can find a mod 2 d+1 chain whose boundary is that cycle. And I should have said this is I'm going to take a cellular cycle here. I want to avoid local issues. So all my stuff. So from here on out, all my cycles are going to be cellular cycles, which is to say that they are sums of faces in the unit grid in Rn. If I have a cellular d cycle, I can fill it with a cellular d+1 chain. That filling is typically non-orientable, because I started with something that might be non-orientable. In the case of the Klein bottle is a cylinder with the ends glued together by a twist. I can fill that with a mod 2 d+1 chain by taking a solid cylinder and then gluing the ends together with a twist to get a twisted solid torus. That's going to be my F. And like I said, typically this is going to be non-orientable, but we can cut it. We can cut that twisted solid torus into orientable pieces. In this case, just a ball, to get a lift of F with integer coefficients. And then the boundary of that lift of F is a pseudo-orientation of A. That's exactly what we saw with the Klein bottle. We take this twisted solid torus, we cut it to get a ball. The boundary of that ball is a sphere, and that sphere is congruent mod 2 to the fundamental class of the Klein bottle. And so the difference between the mass of the pseudo-orientation and the mass of what we started with is roughly how much of F we had to cut, how much of that d+1 dimensional object we had to cut in order to make it orientable. Okay? So, so again, let me start by showing you an example of how this works. In this case, before the easiest example was dimension 0. Here, the easiest example is codimension 1, because if you have a cycle which is codimension 1, then it's easy to orient it, because if you have a cycle that's codimension 1, then it's the boundary of something top dimensional. And if we have something top dimensional, we can orient it just by inheriting an orientation from Rn. So that top dimensional chain is orientable. That gives us an orientation on its boundary, which is A. And since A is orientable, its non-orientability is just equal to its mass. And in particular, this is why we get an identity in R3. Because if you have any surface in R3, it has an inside and an outside. If instead of embedding the Klein bottle in R4, you immerse it in R3, so you have this self-intersection here where the neck intersects the bulb, then it has an inside and an outside. If you imagine a fly inside the bulb, it can't fly out that way because the bulb is in the way, and it can't fly out through the neck because of the self-intersection, because if you go out the neck, you're just going to run into the outside of the bulb. So the inside of the immersed Klein bottle is a shape that looks like this. We have this sort of torus region, the solid torus region in the bulb, and then you have a projection out into the neck, but that's capped off right here where it runs into the outside of the bulb. That is topologically just a solid torus. A solid torus is orientable. The boundary of the solid torus inherits that orientation, looks like this. And so this gives you an orientation of the immersed Klein bottle. Basically, you just cut along that self-intersection, and then you get a you get a solid torus. You get the boundary of a torus, or you get a torus, and you got this neck which is capped off by that piece of the self-intersection. So Klein-Bottle has an inside and outside, so it's orientable. In general, any n-1 cycle in Rn has an inside and an outside, it's orientable. And so the non-orientability of A is equal to the mass of A for any n-1 cycle A. In particular, if T is an integral n-2 cycle in Rn, then the filling volume of 2T is twice the filling volume of T. And this is in particular when n is equal to 3, then T is an integral, is a 1 cycle, and so the filling volume of a 1 cycle in R3 satisfies this identity. Okay? Okay, so what about higher codimensions? So what I'm going to do is I'm going to give you a bad argument in high codimension, and then a better argument, and then the argument that gives you the constant factor. So the bad argument is this. Say I have a mod 2 cellular D cycle of mass V. I'm taking cellular cycles again, so I don't have to worry about local issues. Say I have a mod 2 cellular cycle of mass V, then by the isoparametric inequality, I can fill that with a mod 2 chain of volume of roughly V to the D plus 1 over D. And that mod 2 chain is a sum of unit cubes, a sum of about V to the D plus 1 over D unit cubes. And so if we want to cut it into orientable pieces, we have all those unit cubes. All those unit cubes are orientable. So we cut it into those unit cubes. We orient those cubes at random to get an integer filling, f sub z. And then we take the boundary of f sub z to get a pseudo-orientation of our original cycle A. Now, the problem is that whenever you have two neighboring cubes in that filling, the probability is 1 in 2 that you're going to have one orientation on one of the cubes and the opposite orientation on the other cube. And so each of the boundaries of those cubes has a probability of 1/2 of showing up in that pseudo-orientation. So your best estimate for the size of the pseudo-orientation is that it's bounded by the mass of the boundaries of all those cubes, which is roughly V to the D plus 1 over D. And so this is a very simple argument. We take this filling, we cut it into a bunch of orientable cubes, and we just orient those cubes at random. But it's not very efficient. Remember, our goal is to get a bound of order V. So how can we improve this? So the first thing is that because we cut the filling into a lot of little tiny pieces, little 1-by-1 cubes, the boundary of those cubes is very large. So the first thing we can do to improve this is to try to use use bigger cubes, fewer cubes, but bigger cubes. So rigorously, what we can do is this. Instead of just constructing a filling made up of a whole bunch of unit cubes, we construct a sequence of approximations of our original cycle. So here's our original cycle in the 1-by-1 grid. Here's an approximation in the 2-by-2 grid, in the 4-by-4 grid, and we can keep on going, 8-by-8, 16-by-16, and so on. Eventually, our grid is going to get larger than the original cycle. Eventually, the approximation in the 2 to the 100 by 2 to the 100 grid is going to be 0. And that's going to take about logarithmically many steps in order for the cells of the grid to get bigger than the original cycle. So we've got logarithmically many approximations like this. We can then connect one approximation to the next with a bunch of little cubes. So for instance, here's the 1-by-1 grid, here's the 2-by-2 grid. Those have to be close together. Those have to be a distance about 1 apart. And so we can connect one to the other by just sort of walking around the original curve, the curve in the 1-by-1 grid, and just making little edits, just shifting the curve left or right or up or down by 1 unit to get it to this approximation. And that's going to result in a picture like this. The region between those two approximations can be filled with a bunch of 1-by-1 squares. And how many do you need? Well, like I said, you just kind of walk around and you add squares as necessary to go from one grid to the other. That's going to take about V squares, and each of those squares is 1-by-1, has perimeter on the order of 1. Then the next step, we want to go from the 2-by-2 grid to the 4-by-4 grid. Again, these are close together. These are about distance 2 apart. And so again, you can go from here to here by just walking around this approximation and then just shifting the approximation up or down or left or right by 2 units to get the approximation in the 4x4 grid. And so again, you get a collection of 2x2 cubes now. And because this approximation is made up of about half as many segments as this approximation, you only need about half as many squares in order to do that. And you're going to, so you repeat this for A3, A4, A5, all the way up to A sub log V, because A sub log V, you're going to get 0. And if you then add all these annuli together, you end up with a filling of A, which is made up of a bunch of squares of different sizes. In practice, what you end up with is you have log V many approximations that are each connected by one of these annuli. In each annulus, well, as you increase in scale, you start with V squares with perimeter about 1 each. Each time you go up in scale, the perimeter doubles, but the number of squares roughly halves. So at each scale, you're using about the same amount of boundary, using about V boundary at each scale. And because they're about log V scales, you can conclude that you have a pseudo-orientation of A whose mass is at most a constant times V log V. So this is better. This is an improvement on what we had before, but we're still not where we want to be. Remember, we want this to be just that the mass of the pseudo-orientation is bound by a constant times V. We want to get rid of this log factor. So how do we get rid of this log factor? Well, if you look at this algorithm and you ask, where is this inefficient? Where are we wasting boundary? It turns out that really the place where we're wasting boundary is regions where regions where A is flat. Because at places where A is flat, say we have some piece of A, which is just say a diagonal line like this. Places where A is flat, then the 1x1 approximation is some diagonal, is a staircase like that, and then the 2x2 approximation is a bigger staircase like that. And then the 4x4 approximation is a bigger staircase like that. And then the 8x8 approximation is a bigger staircase like that, and so on. And so when we break this up into cubes, we're getting, about, if this has length L, we're getting L from the 1x1 approximation, then another L from the 2x2, another L from the 4x4, another L from the 8x8. We have log many approximations, and so we get L times log L. But that's really kind of a waste, because remember, we're not really trying to break the filling up into cubes. We're trying to break the filling up into orientable pieces. And if our original surface was flat, then that's orientable. We can stick an orientation on that original piece of the surface. And if our original surface was flat, we can stick that same orientation on all of the approximations as well. And so if we want to break it down into orientable pieces, it's overkill to break it down into all these squares of different sizes. We might as well just break it down into, say, the 1x1 approximation, and then the 8x8 approximation, and just draw a big triangle like that. So in order to get rid of that log factor, what we have to do is we have to figure out where we can skip approximations like that, where we can just jump straight from the 1x1 approximation all the way up to the 8x8 approximation. We need to find places where our surface is flat, because at places where our surface is flat, we can do better than just approximating logarithmically many times. Is this okay so far? Okay, how much time? Okay, a little bit. And the problem, though, is that we have no guarantee that there are places like this. We have no guarantee that our surface is ever close to a plane. We can construct examples that are never close to a plane. So for example, let's construct a surface. So let's start with, say, oops, I'm off the page. Okay. Let's start with, say, a cube. And this is going to be a big cube. This is going to have side length roughly V. or sorry, roughly root v. So the area of the cube is going to be on the order of v, where v is quite large. Because remember, we're trying to construct a cellular cycle here, so I need to start with something very large so that I have plenty of room to work with. Once I have that cube, I'm going to make it non-orientable. I'm going to cut out disks in the faces, and then I'm going to glue on cross handles. I'm going to connect them by a cylinder and glue that cylinder with a twist. And I do that on the top. I do that on the side here. I do that on the other side here. I have back and left and bottom and so forth. But eventually I run out of space to add those handles. Eventually I run out of space to add cross handles. So I have to stop. But the thing is that even if I've run out of space to add on cross handles that are this big, there's still room to add on smaller cross handles. I can take, say I go down to a smaller scale, and I add on a smaller cross handle like that, and then another one over here, and another one over here. Basically, wherever I find somewhere on this surface which is flat, I cut out two disks and I glue on a cross handle, right? Eventually, I'm going to run out of room to do that again, and so then I can do the same thing at an even smaller scale. I can go to an even smaller scale and glue on even smaller cross handles, and so on and so forth. As long as I want, actually not quite as long as I want, because I started with something with side length root v, and if I want it to be cellular, I can't go down to scales below 1. So I can do this as long as I want, as long as my scales stay between root v and 1. So what does this produce? This produces a cube plus a bunch of cross handles. And we have roughly, say, 6 cross handles of diameter, say, about root v. And we have, say, and say our next scale is, say, 1/10 of that is root v over 10. That means that we have enough room to add 600 cross handles of diameter root v over 10. And then let's say our next scale under that is, say, root v over 100, another factor of 10. We can have, say, 60,000 cross handles of diameter root v over 100. And we can keep on going. If we go down by a factor of 10 each time, then we can keep on going until root v over 10 to the n is about 1. So we can do this about log v times. Right? And this is a surface which is never close to a plane. At least it's never close to a plane on any scale between root v and 1. And because it's never close to a plane, its non-orientability can be very large. If we try to figure out how to make this orientable, in order to make this orientable, we need to cut all of these cross handles. We need to cut all the small cross handles and all the bigger cross handles and all the biggest cross handles. We need to, in order to find a pseudo-orientation of this surface, we need to cut everywhere. And so if you calculate the non-orientability, what are you going to see? Well, that non-orientability is going to be made up of those 6 cross handles of diameter on the order of root v. Those are each going to contribute about v to the non-orientability. Those 600 cross handles of diameter 1/10 of that, those are each going to contribute about root v over 10 squared. So v over 100 to the non-orientability. And then those 60,000 tiny cross handles of diameter root v over 100. Those are each going to contribute about v over 10 to the 4th. And so what we end up with is a total non-orientability of 6v plus 6v plus 6v. I guess all these things are approximate. Total non-orientability of 6v plus 6v plus 6v, and so on and so forth, log many times. And so we end up with a total non-orientability of v log v. And so this is really this is really an example where you do in fact need to worry about all of those scales, where you do in fact need to worry about, well, you have logarithmically many scales, where at each scale you need to do a substantial amount of cutting, where at each scale you have to do about v worth of cutting. And so this is an example where you really see why that v log v in the approximation theorem is necessary, because you can have about this many scales and you can have about this much cutting to do at each scale. But remember, our theorem was that this can't happen. Our theorem was that if you start with a cycle of volume v, then it has a pseudo-orientation of mass order v. Why does this not violate that theorem? Well, it turns out that as we did this, as we added all these cross handles, the area of the surface increased at the same time. Because when we added these 6 cross handles of diameter root v, so well, I mean, we can track it. I mean, we have the area of this A. We started out with this cube, which had area 6v. Then again, we added these 6 cross handles of diameter roughly root v. That's going, each of those are going to add about v to the area. So we're going to get 6v from those cross handles. We're going to get another 6v from the small cross handles. And we're going to get another 6v from the 600 tiny cross handles. We're going to get another 6v from the 60,000 tiny cross handles, and so on and so forth for those log v many scales. And so what we're going to end up with is going to end up with area roughly 6v times log v plus 1. Because every time we did this, we added some extra area. As we increased the topological complexity, we also increased the area. And this is Thomas. This is where this is what I was saying earlier about what I think might be optimal. Is that, well, optimal is not necessarily finding the best Klein bottle, because the best Klein bottle is only non-orientable at one scale. Optimal is probably about figuring out the best way to take a flat piece of a flat surface and then glue on something non-orientable to it. To take a flat surface and glue on a cross handle to it. Because if you can do that, and if you can do that over many different scales, then you get something with non-orientability like v log v and area like v times v log v plus 1. And so you're going to get a little bit of a bump from having those multiple scales to work with. But again, I haven't done any calculations to try to figure out what the best way to add a cross handle to a surface is. Is this okay so far? Are there any questions about this so far? Okay, I'm running a little bit over time. Do you want? I do want to say a little bit more. I do want to get to the decomposition here. But if you have somewhere else to be, please feel free to just pop out. And I guess the recording is still going to continue. But are there any questions about anything so far? Is it okay if I go over a little bit?
Yeah, I think you certainly for me, yes.
Okay, yeah, like I said, feel free to drop out if you if you have to. So we do have this problem that we can have surfaces that are never close to a plane, and so we do have to figure out what to do with those. We do have to figure out how do we prove this proposition for sets that are sort of complex, that are sort of far from planes at many different scales. And the basic strategy is like this. What we're going to do is we're going to take our complex surfaces and we're going to decompose them into simple pieces, into pieces that are usually close to a plane. And then we're going to try to prove the theorem for those simple surfaces, to try to prove that if you have a surface that's usually close to a plane, then it satisfies this bound on the non-orientability. So specifically, the notion of a simple surface that I want to use here is based on uniform rectifiability. So uniform rectifiability is a concept due to David and Sems. What it is, it's a quantitative notion of the idea of rectifiability. It's a quantitative version of rectifiability. The thing is that rectifiability is an infinitesimal phenomenon. One of the definitions of a rectifiable set is that it's a set that has a tangent plane almost everywhere. And so that condition only pays attention to what happens at infinitesimal scales. It doesn't pay attention to what happens at larger scales. And so in particular, if you take an example like this, which is complicated at every scale, but it's cellular, it's made up of unit cubes, then this is rectifiable because, well, it's made up of unit cubes, and those unit cubes are, they have a tangent plane everywhere on the interior of the unit cube, and the only place where this surface doesn't have a tangent plane is at the boundaries of those unit cubes, but the boundaries of those unit cubes are lower dimensional. The boundaries of those unit cubes are measure 0, and so this is rectifiable, even though this is not really flat at any scale above 1. So uniform rectifiability is a way of defining what it means for a surface to be usually close to a plane. And there are a lot of definitions of uniform rectifiability. There are directions that translate this notion of being usually close to a plane very directly. But for the purposes of this talk, for the purposes of this work, I need a slightly more complicated definition, which is a definition in terms of what are called corona decompositions. A set is uniformly rectifiable if and only if it has a corona decomposition. The full definition is quite complicated, but the rough idea of a corona decomposition is that a corona decomposition consists of a few, not too many Lipschitz graphs, such that for all but a few balls B, the intersection B intersect E is close to one of the graphs. So the standard example that I give is if I have a square. If I have a square like this, then I have a few Lipschitz graphs, namely one for each side of the square, so that if I take a random point on the square and take a ball around that point, then probably that ball doesn't intersect doesn't hit one of the corners. And if it doesn't hit one of the corners, then the set coincides with the Lipschitz graph inside that ball. Which Lipschitz graph depends on which side of the square you're on, but it coincides with one of the Lipschitz graphs. The only problem is that if you choose one of the corners, or if you choose a point that's close to one of the corners and you take a ball that's large enough to include that corner, then you run into a problem, but those problems are rare in a sense that you can quantify. On the contrary, if you take the surface we were looking at before, this is a very complicated surface, and you can't really approximate it by a few Lipschitz graphs. If you wanted to approximate this by a bunch of Lipschitz graphs, sort of the best you could do is, well, maybe you could take this is a cellular surface, maybe you could take each of the individual squares, and that's a Lipschitz graph. Or at the very minimum, you would kind of need some Lipschitz graphs for the original cube, and then some extra ones for each of the tiny handles, and each of the small handles, and each of the big handles. You would need a lot of Lipschitz graphs, and that goes counter to the spirit of this definition. That's too many Lipschitz graphs. But once you have, so you can define a notion of uniform rectifiability that makes this precise. And then the proof of the proposition is based on two pieces. One, a decomposition result, that if you have a mod 2 cellular D cycle A, then you can write it as a sum of simple mod 2 cellular D cycles. You can write it as a sum of mod 2 cellular D cycles with uniformly rectifiable support. And furthermore, that decomposition satisfies this bound. The total mass of the pieces of the decomposition is at most a constant times the mass of the original surface. The idea of how this works is that if you have pieces of your surface, the idea of how this works is that you start at small radii and you move up to larger and larger radii. So by basically looking for regions of your surface that are too complicated. If you find a region of your surface that's too complicated, say you find one of these tiny cross handles here, then you can just replace that piece of the surface with something simpler. You can just replace that with, say, a minimal surface. That gives you one piece of your decomposition, And if you repeat this, if you keep on looking for small balls where your surface is complicated and then replacing them with simpler pieces, you can just progressively get rid of the complexity of your surface. You start at the small scales, you get rid of all these tiny cross handles. Once you've gotten rid of all the tiny cross handles, then any ball of about that scale is relatively simple. So you move up to the next size scale of ball. Now, if I have a ball that's this big, if that ball contains one of these handles, it's too complicated. Let's just replace it with something flat. And that produces another piece of the decomposition, and it makes the surface a little bit simpler. We repeat that every time we see one of these small cross handles, we replace it with something flat, and that produces one piece of your decomposition for every small cross handle and simplifies your surface. Now, all balls about this size are simple, and so you move up to another scale, so you move up to the next size. Now you look for balls about this big that are complicated. Whenever you see a cross handle, whenever you see a ball like that that contains a cross handle, you can again flatten it out, produce another piece of your decomposition, and then move on. Eventually, this process just eats up all the complexity of your surface, and what you're left with is one big simple piece, and that's the last piece of your decomposition. So that's a very quick sketch of this decomposition result. You can take something complicated, and then you can just go from small scales to large scales and break it up into simple pieces. I guess I should say that in the case of the cube example, the decomposition you end up with is roughly the original cube plus, a piece for every big cross handle, and then pieces for each, plus pieces for each of the small cross handles, plus pieces for each of the tiny cross handles, and so on and so forth. And the total area of all these pieces, each of these scales, our scale goes down by a factor of 10, but the number of pieces grows up by a factor of 100. And so the contribution from each of these scales is on the order of V. And so the total area of all the pieces of the decomposition is on the order of V log V. It's on the order of the area of the original complicated surface. So you can take your complicated surface, you break it up into these simple pieces with uniformly rectifiable support. That's part one of the proof. Part two is then to deal with all those pieces with uniformly rectifiable support. To show that if you have a mod 2 cellular cycle with uniformly rectifiable support, then it has a pseudo-orientation whose mass is bounded by a constant times the mass of the cycle. This is this uses the fact that a uniformly rectifiable set is flat at most regions, at most points, and most scales. This is a uniformly rectifiable set is usually flat. And like we said before, if you have a piece of your surface which is flat, you can do something like this. If you have a piece of your surface which is flat, then you can skip from one approximation to another approximation at a much larger scale. And so the idea of this bound is to use the corona decomposition, use the fact that at most pieces of your surface can be approximated by Lipschitz graphs. Most pieces of your surface can be approximated by orientable pieces to construct your pseudo-orientation, to break up this filling into orientable pieces. Sorry, this is a very brief sketch of the proof. If anyone's interested in more detail, please feel free to ask about it. But this is just I just wanted to give you a rough idea of the strategy here today. Okay, is this okay so far? Are there any questions about any of this so far? I just have one slide left. So the last thing I want to do is I want to mention, okay, where can we go from here? So like we talked about earlier, one natural question is whether we can get a good bound on this constant C, in particular, whether we can show that the filling volume of 2T is always greater than or equal to the filling volume of T. Like I said, this is completely open. The methods I've talked about today give you some bound, but it's going to be some very, very small constant. And in fact, that constant is also going to depend on the fact that we're using 2 here. And these same arguments work with 2 replaced by any k, but then the constant depends on k. So we end up showing that the filling volume of kt over k is at least some constant times the filling volume of t, but that constant depends on k. So this inequality is not very helpful. It would be very nice to be able to choose this c sub k uniformly. It would be very nice to be able to say that the filling volume of k times kt over k is at least some constant times the filling volume of t. That would let you relate real filling volume and integer filling volume, which as right now we have no way of doing. But this is also completely open. And then finally, a broader question. You can define this notion of the non-orientability of a surface pretty generally. We defined it for surfaces embedded in Rn, but any surface, any metric space embeds in L infinity. And so you could define the non-orientability of an arbitrary surface, of a Riemannian surface, by embedding it in L infinity by an isometric map, and then looking at non-orientability in L infinity. And you can construct surfaces that have larger non-orientability than what we've constructed here. You can construct surfaces that have larger non-orientability in L infinity than just linear. You can construct surfaces with you can construct a surface of area 1 with arbitrarily large non-orientability in L infinity. So in a sense, this tells us that there's something special about surfaces that embed in Rn. There's something special about surfaces that are that embed in Rn by, say, a bi-Lipschitz map. And so one question that I like to ask, but I don't have really good answers for, is the following: what can we say about the geometry of surfaces that embed in Euclidean space by a bi-Lipschitz map? In general, like there are various notions that a sort of generic surface or a generic graph has expander properties, but things embedded in Rn don't have expander properties. Can we say things about, can we say things like that? Can we say things? I guess one of the questions that I ask here is that if you have a surface embedded in Rn, then it has a Pants decomposition. Typically, if you draw surfaces in, if you draw a surface, if you draw a picture of a surface, you can construct a relatively small Pants decomposition of that drawing of a surface. Surfaces that embed in Rn by a bi-Lipschitz map are kind of surfaces that you can draw a pretty accurate picture of. Do those have particularly efficient Pants decompositions? We don't know. As far as I know, it's an open question, and so yeah. Okay. Anyway, I think I'm out of time, so that's all I wanted to talk about.
Thank you. Questions?
I have a question. Can I go?
Yeah,
Yeah.
please.
Things are related to any other invariants. It looks a lot like maybe an eigenvalue problem connected with them. The reason I say that, well, firstly, there are these theorems that I'm sure you're familiar with of Guth and Lubotsky relating filling to expansion and coding in certain hyperbolic manifolds. But there's an old theorem of Peter Doyle, was a conjecture of Phillips and myself, that if you put any circles in the plane, any number of circles, wherever you place them, and then you fill up the circle, you treat those circles as, go to hyperbolic 3 space, put hemispheres over each circle, assume they disjoint.
Okay.
Now you have a hyperbolic 3 manifold with boundary, but of course the boundary is very complicated because I don't limit the number of circles. And then I ask about the smallest eigenvalue of the Neumann Laplacian on the complement. And this is universally bounded below, independent of where you place the circles.
Okay.
Or how you place the circles. So this was proved by Doyle. And the argument has got a lot of similarity with yours. It's kind of a filling thing, and then you have to argue it scales, and then. So I'm wondering if there's and you mentioned the word expansion. I don't know if what you meant by that exactly, but it looks like the combinatorial analog is somehow related to cuts of manifolds, which looks like an eigenvalue problem to me. Do you know any connection in that way, right? So,
I mean, the origin of corona decompositions was a problem. It was a problem about analytic functions. So I'm not surprised that so it sounds very neat that it sounds very reasonable that you could use things like this also in hyperbolic 3 space. I don't know. I don't know whether there's a way to turn this into an eigenvalue problem.
I guess if Guth doesn't know, he knows both fields rather well.
Yeah.
But it does look like it, and a lot of the arguments are similar. Like you're working up to a constant, and you're looking at all scales. Mm-hmm. I'll send you a copy of Doyle's paper.
Yeah, that would be very interesting.
Very interesting, anyway.
Do you expect actually the answer to the first question to be yes?
I guess I kind of do, but I don't feel. I feel like I expect it to be yes, but I feel like I expect it to be yes for sort of not for a really good reason. Like I expect it to be yes, kind of just because like if you construct a nice looking cross handle or a nice looking project cross cap and glue on top of a vertical on top of a plane, I kind of expect it to be, you know, the extra area of the cross cap is probably bigger than the area of the thing that it takes to cut the cross cap. So I kind of expect the answer to be yes, but I don't expect there to be a really good reason for the answer to be yes, if that makes sense.
And I mean, like at this point, once you have your hard bound, no? I mean, can't you just think there's maybe a minimize? I mean, like, does it make sense to actually ask the question, is there a minimizer for your problem? Like, you know, something which has fixed mass, but minimizes the, like, you see, some kind of variational problem that maybe identifies
right
candidate, which might have which might have actually better properties because I don't know, it's a minimizer.
Right. So what I expect is kind of so certainly you can ask these questions for arbitrary currents in Rn. If you add some sort of regularity that'll smooth it out below some scale, then I kind of expect, and like because of this construction with all the different scales, because this ratio is kind of getting better as you add more and more scales, I kind of expect that the extremal example is going to try to take advantage of as many scales as possible. So it's not necessarily going to be a nice extremal example. Where I do think there could be nice extremal examples is sort of if you fix. The problem I think where there could be a nice extremal example is if you take a plane and you add a well, I guess if you take a unit circle and you add and you look for crosscaps whose boundary is the unit circle, crosscaps embedded in R4, say, whose boundary is the unit circle, and then you try to look at the ratio between the additional area of the crosscap, the area of the crosscap minus the area of the unit circle, divided by the smallest amount of area necessary to cut the crosscap.
And that one you can probably solve by Douglas-Rado, I would imagine.
You'll have to. I don't know. I don't know that. So you have to tell me about
Because
that.
you have fixed the topology of your guy, and you're minimizing.
Yeah.
Right.
Yeah. It could very well be, at least, and certainly I would expect to be able to find some numerical solution. But like that would, if you solve that, that would at least give you give you an idea of what this what this constant might be.
Well, the composition of David and Sams is not effective, though. No, I mean, the bound on the mass is pretty bad, I guess.
Yeah, I think a lot of their constructions are effective in the sense that you can get some constant out of them, but like it's going to be some terrible constant.
Yeah, it's going to be pretty bad. Okay, if there are no other questions, thanks, Robert, again, and I guess we see each other for the next analysis seminar next Monday with Lior, right?